Kelkar from City International School, and today we are going to do the topic lens, right? From the chapter light reflection and refraction. Okay, the topics which we are going to cover today is images formation in lenses, then sign convention for lenses, lens formula and magnification, power of lenses. Okay, students, so let's start. Now, what are lenses, right? You must have heard this word even in our eye. In our eyes, there are two lenses in two different eyes, right? So, what are these lenses, right? So, let us see more about lenses. The transparent refracting medium. So, lenses are the transparent refracting medium bonded by two surfaces in which at least one surface is curved is called lens, right? Here we can see that if I see this lens, right, at least one surface is curved, so I can say that this is a lens. But otherwise, in our studies, we are going to take a biconvex lens. It has two curved surfaces, and if you see here, these two curved surfaces we got from the two spherical lenses, right? So these surfaces we got from the two spherical lenses, right? And these two are bulging surfaces, so that is why they are biconvex lens. This one is a plano concave lens where one surface is concave, it is a cave like, and the one is plane, right? This is biconcave lens. This we are going to study in our syllabus. Okay. So this is all about the lenses of concave and convex lenses. Let's see more about concave and convex lenses. This is a concave lens. It is also referred to as diverging lens. We are going to see more about it, right? Now the lens surface is concave in nature. As you can see, this surface is concave. This is making a cave, right? And it is also a part of two different spheres, right? So that is why we call it a concave lens. Okay, this is a concave lens. It is also known as diverging lens. Now let's say how what is the reason behind the lenses? Why do we call converging and diverging lenses, right? If you see concave lens, if you have seen concave lens carefully, it is thicker at the center, right? This part is thicker at the center, and as you go at the end, they are tapering. Okay, they are not thicker, they are thin at the corners, thick at the center, right? Now in case of concave lens, lenses are thin at the center and they are thick at the edges are broader, thicker and thin at the center. Now if you see all the lines reflected rays are converging at one point, right? So we call we call convex lens as a converging lens, right? Whereas if you see this concave lens, okay, let me take pen. If I see this, if you see this concave lens, this is a ray, right? It is getting diverged from this point, right? Okay, so it is getting diverged. If I going to extend it at the back, all these rays, okay, they are getting diverged. Here also this ray, this ray is a principal axis ray, it will go straight. This ray again, it is getting diverged, but if I am extending it, they are appearing to converge at a point, right? So we call that concave lenses are diverging lenses, whereas convex lenses, you can see the all rays are converging, they are meeting at one particular point, right? And what do you observe in this ray, children? The ray which is coinciding the principle of axis. Is there any divergent or convergent in this ray? No, this ray is going straight. Okay, so uh, now in case of convex lens, the focus is a real focus, right? convex lens focus is a real focus. Why it is real focus? Because rays are meeting at this point. Okay, it is in reality, this is happening in reality. If you keep a, you know, if you keep a plane over here, you will find the images formed on this screen. Clear? In case of concave lens, it has a virtual focus. It means it seems that rays are moving out from this point, right? Rays are coming out from this point. So that is why we call that this focus is a virtual focus in case of concave lenses, right? It converges the parallel beams of light on refraction through it. This we have already seen. It diverges the parallel beam of light on refraction through it. Okay, so these are the different characteristics of convex lenses and concave lenses. We have already done concave mirror and convex mirror. Okay, in case of mirrors, concave mirrors are converging and convex mirrors are diverging. So the case of lenses are absolutely opposite of what we have done in case of mirror. Okay, now the terms related to lenses, these are terms are quite similar to the terms which we did in concave and convex mirror. Okay, so let's see the terms. The lens has two spherical surfaces. We have seen that these are the two spherical surfaces, right? The lens have two spherical surfaces. Yeah, these are the two spherical surfaces. Fine. And a line is passing through this surfaces, right? Now what do we call this? The center of the sphere is called the center of the curvature of the lens. The center of the sphere, suppose this is the center. Okay, this is the sphere, right? Okay, the center of the sphere are called the center of the curvature. So in case of lenses, we have two center of curvature. This is C1 and C2, because this lens is made up of two spherical lenses, right? So definitely it has two center of curvature, right? The center of curvature on the left hand side is C1. We also call is 2f1. Why 2f1? Because center of curvature is double of f1, right? Now what is f1? F1 is a focus. It's just like a focus, right? Okay, now f1 is a focus on the left hand side. C1 is a center of curvature on the left hand side, right? And the distance from C1 to the optical, now this center of this lens is a optical center, and it is denoted by the capital letter O. So O is the optical center, right? And the distance from O to C is known as radius, and the distance from O to F1 is known as focal length. In case of convex mirror, I'll be considering the distance between O and F2, that as a focal length. Children, here it should be you should pay more attention. The distance between O, optical center O, and F2 in case of convex lenses will be considered as focal length. Why? Because when the rays coming parallel to the principal axis, they are going to meet actually at focus. So this focus is also known as the principal focus. Okay, children, and this is f2 on the right hand side, the back side of the lens, as you can also say, right? F2 is a principal focus, and C2, which is also known as 2f2, is the center of curvature of my second sphere. Okay, now we have done with the center of curvature, right? C1 and C2 are the two different center of curvature. You can see here C1 and C2 are the two different center of curvature. If you measure the distance, if you see the C1 from O, it is nothing but the radius of the first sphere, and O and C2 is the radius of the second sphere. Okay, principal axis, the line which is joining C1 and C2, straight line. Okay, and it is passing through the optical center also. This line is principal axis, right? O we have already discussed. This is the optical center. The center point of the lens is the optical center represented by the capital letter O. Aperture is the effective diameter of the circular outline. Okay, it is effective diameter. Hmm? So from here till here. Okay, so this will be the diameter of the circle, right? From here till here, this is the diameter, or it can be from here till here, right? So we consider the vertically. This is a diameter, which is a aperture. Focus, we have already seen the focus. So when the rays parallel to the principal axis, whenever there is a ray which are parallel to principal axis, they meet, okay, or they seems like to coming out from a particular point, that is known as focus, right? Okay. So let's take the first case, convex lens, right? So when ray parallel to the principal axis get refracted by the convex lens, they converge to a point on a principal axis. Okay, they converge to a point on a principal axis. We have seen in the last diagram, right? So if I make some ray to pass which coming out from the object parallel to the principal axis, they seems to converge at focus, right? So for every dot object I need to take two rays. Here I just have taken one ray, but we are still to do the images. So this is just to explain you all, right? So they converge at a point on a principal axis. This point is known as principal focus. This is a very new point in lenses, right? Wherever they are converging, okay, on the principal axis, in case of convex mirror, it is a principal focus. Clear, student? Okay, if you pass a parallel ray from opposite side of a lens, you will get another principal focus on the opposite side. Okay, if the ray is coming from this side, okay, so you will get a focus on this side. So if the ray are coming from the opposite side, this will be f1 will be the principal focus. So what we have concluded in this, so wherever the rays are converging, in case of convex mirror, wherever the rays are converging, that particular point on a principal axis is known as principal focus. Okay, students? Okay. In a lens has two principal focus, usually named f1 and f2. So here we have we will follow the rules which are given in NCERT. All the diagrams will be followed according to the NCERT. So on my left hand side I have got f1 and c1. On my right hand side we have f2 and c2. So there are two foci and two center of curvature. Okay. Now, when the ray parallel to the principal axis get refracted by concave lens, let's take the case of concave lens. Let's take this case. Okay, okay, they appear to diverge from a point on the principal axis. This point is principal focus. Now, if I draw a ray over here, right? Okay, at this point they will get refracted. Okay, but if I extend it back, you will see that this ray is appearing to coming out from the f1. It appears to diverge from a point on principal axis. It appears that the rays are coming from the f1 or diverge from a point on a principal axis. So this one is my principal focus. So as you have seen here, okay, not to get confused, on my right hand side this is right and this is left, right? So on my right hand side I am getting a principal focus in case of convex lenses, and on my left hand side I am getting a principal focus on concave lenses. So these points you should remember. Let's see the different rules in lenses. Okay, convex lenses and concave lens. Let's see the rule number 1. A ray of light which is originally parallel to the principal axis, after refraction it passes through the focus. Now this is a principal focus in case of convex lenses, right? Or in case of concave lens, a ray of light which is originally parallel to the principal axis will appear to coming from the principal focus. See, it is appearing that it is coming from the principal focus. So these are the two rules in case of convex and concave mirror. This is rule number 1. Now coming to rule number 2. Sorry, it should be 2. This should be rule number 2. This is rule number 2. And this is rule number 3. Clear, student? So in case of rule number 2, when a ray of light initially passing through the focus, right, it passes through the focus to the convex lens, then it becomes parallel to the principal axis after refraction, right? So after refraction, you see that this ray is no more going in this direction. It is parallel. This is my principal axis and this ray is parallel to the principal axis. Clear, student? Now in case of concave lens, a ray directed to the focus. This ray is directed. It seems that it is directed to the focus. It seems that it is going towards the focus, right? So after refraction, what will happen? After refraction will emerge parallel to the principal axis. Okay, a ray directed towards the focus seems to directed towards the focus. After refraction becomes parallel to the principal axis. This is my principal axis, and after refraction it gets parallel to the principal axis, right? Now the third rule, a ray of light passing through the optical center of a convex as well as concave mirror, right? Here the convex mirror, if you see this ray of light passing through the optical center, in both the case they are passing through the optical center, okay, but goes straight. There is no deviation. It doesn't deviate. If you see, the ray is not deviated. So there is no deviation when a ray is passing through the optical center, right? These rules are very important for the formation of images. So let's take the images. So let's take the first case where the object is at infinity. Here the object is at infinity and we are going to take the rule. Okay, infinity, I can make this sign also of infinity, right? So if whenever there is an object at infinity, you just have to take two parallel rays. Okay, there are two parallel rays from either side of the principal axis, and in case of convex mirror, because we are doing convex lenses. So in case of convex lenses, after refraction, children don't write reflection here, you need to change the word reflection with refraction because we are doing lenses. So in case of lenses, after refraction, okay, this ray is diverged towards the principal focus, right? This is my principal focus. This is my right hand side, as I told you, principal focus and 2f2, that is center of curvature. Over here will be f2 and 2f2. This is center of curvature C2. Okay, why we have written 2f? Because center of curvature is double of focus, right? And here is f1. On the left hand side is f1 and C2, or C2 can also be written 2f1, right? Okay, now in case of the object where the object is at infinity, I have taken two rays. It is very important to take two rays if you want to form an image, right? So they are parallel to the principal axis. This is my principal axis. After refraction, it diverged and after refraction it converged at a point f2. Okay. Okay, now let's see the position and the size of the image. Position, as you know, is the position of the images at focus f2. You can also write at principal focus, right? Or f2 is also fine. Size of the image, you can see it is a highly diminished point size image. The nature of the image is real and inverted. Children, the cases which we are going to discuss in convex lenses, it is very much similar to the cases which we discussed in the images which we discussed in concave mirror. Okay, so concave mirror and convex lenses images, the position and the nature of the images are absolutely same. Okay, but the way of drawing the diagram is different. Okay, here we have got two focus and two center of curvature. Clear? So coming to the next, where now you can see the object has come little closer. Initially the object was at infinity, we couldn't able to see the object. Here the object has come little closer, but it is beyond 2f2. Beyond 2f1. 2f1 is nothing but the center of curvature. Okay, center of curvature 1. This is the center of curvature. So now the object, we have to take the two rays. First ray, which is parallel to the principal axis, passes through the focus, or principal focus, right? This is our principal focus. And the other ray, it will be going directly from the optical center undeviated, and you have to just draw a straight line going through the optical center. Wherever these two rays are getting intersect, there image will be formed. This image is what it is diminished as compared to the image of an object. It is inverted, and because it is inverted, we say that it is real and inverted image. Okay, real images can be we can take a real image on the screen. They can be formed on the screen. If I put a screen over here, you will see the image of the object on the screen. Whereas in virtual cases, the image of an object cannot be seen on the screen, children, but our eyes can able to see, human eyes can able to see real as well as virtual images. Okay, now position of an object is between, if you see, it is between 2f2 and f2, right? Okay, and the size of the image is small, nature real and inverted. Next, coming to the object, when it is kept at 2f1, that is, it is kept at center of curvature 1. Okay, now let's take two rays. First ray going parallel to the principal axis. After refraction, it passes through the principal focus. Now the second ray, it is going through the optical center undeviated, right? And there is an image formed which is between between f2 and 2f2. Okay, now this image is formed at 2f2. This image is formed at the second center of curvature. Children, this image is formed at the second center of curvature. I'll write over here C2 so that you can make out this is C2, the second center of curvature, or 2f2. The image is formed. You can see the size of the image is same, but it is real and inverted. Let's take the another case. Here the object is between the center of curvature and the focus 1. Okay, now object is coming closer to the lens, and we will take one ray. It is passing through the principal focus. It was initially parallel to the principal axis, passes through the principal focus. One another ray which is going through the optical center. Okay, and they are meeting over here. So image is formed. Now in this case, the image is formed beyond 2f2, that is the second center of curvature. How is the image? It is enlarged, it is real and inverted. Clear, students? So as your object is coming near to the lens, images are going far from the lens. Now coming to the fifth case where the object is at focus. Now I have kept the object is at focus. Okay. Now if you remember the first case of lens, we have kept the object was at infinity and the image formed was at focus. Here the object is at focus. Now let's see where the image is going to be formed. Okay, I have taken two rays as usual parallel to the principal axis, gone through focus, principal focus, and the other ray going straight from the optical center, right? And they are somewhere in the infinity, they are going to meet. We consider that somewhere in the infinity they are going to meet. An image will be highly enlarged image, highly enlarged image. Of course the image will be real and inverted, and size of the image will be highly enlarged, right? This is what we assume, right? Let's see the last case. The last case is very important case, children. Here this is quite a different spatial case where the image is where the object is kept between the F1 and O. Object is between the focus 1 and the optical center. We have kept an object here, right? Let's take the first ray which is parallel to the principal axis. After refraction will go from the principal focus. This is my principal focus. So after refraction it is going through the principal focus, right? Now let's take the second ray. Now this is my second ray passing through the optical center, right? Okay, it is passing straight through the optical center. As you can see, these two rays are diverging. They are going to diverge more and more as they go longer and longer. As they go back, they are going to diverge more. Okay, they will never meet at any point. So how the image is formed in such cases? In such cases what we will do is we are going to extend these lines. Okay, this ray just extended back, even this ray from here extended back. Now you will see they are going to meet somewhere over here, right? And the image formed over here is erect. So erect image are always virtual, right? That means they cannot be taken on the screen. These image cannot be formed on the screen. So virtual and erect image is formed, and enlarged image is formed. Where it is forming? It is forming between the center of curvature and the first focus, right? Between the center of curvature and the first focus. Position of the image on the same side of the object. This is a very important point. So the position of the image is on the same side of the object. So this is a spatial case, and it is a very important case in case from the point of view of exam, right? All are important, but this is little important, more important. Now let's see, this is a different case. See, we have taken initially that the object was in infinity, so we took two parallel rays which are parallel to the principal axis. Okay, but in certain cases we can take the rays which are parallel to themselves, right? It is not necessary that we have to take two rays which are parallel to the principal axis. Here in this case we have taken the two rays which are parallel to each other. Okay, parallel rays from the top point of distance object, right? The object is at very far, right? So I have taken two parallel rays. Of course after refraction they are going to, okay, they are going to meet a point which is straight down. Okay, which is straight down point. This is a point which is straight down from your F2. This is your principal focus. Okay, they are not meeting here, but they are meeting. If you just extend a line from principal focus, they are straight down. Okay, and if you are taking two lines from like this, if you are taking two lines like this, somewhere they are going to meet two lines which are parallel to each other. I am trying to form this thing. They will, after refraction, they are going to meet, okay, a point which is up towards the which is right at the top of F2, principal focus, right? Children, this diagram is not that great. So this example, I have taken this example for you So that you can understand that it is not always necessary that the two lines which are coming from the two rays which are coming from the infinite object kept at infinity are always not parallel to the principal axis. So let's take the next case. This is the table that you have supposed to draw it in your copy with the ray diagram. See the image formation in concave lenses. So there are only two diagrams of image formation in concave lenses. These image formation of concave lens is similar to the image that we formed in convex mirror. Okay, right. Now shall we start with the first? Here the two rays are coming from the object which is kept at infinity, right? Now these two rays which are coming, which is kept at infinity, okay, the first ray which is parallel to the principal axis, right, this ray will get diverged. After refraction, this ray will get diverged, right. Take the second ray also. After refraction, it will get diverged, right. Then from there, just extend the first ray back, produce the first ray back and the second ray also back. Wherever they meet, this is the principal focus of concave lens. F1 is the principal focus of concave lens, right? And F2 was a principal focus of convex lenses according to the CBSE book, what they have given in the book, right? So remember these points and it will help you to avoid any kind of confusion. So please follow your own book and the rules given in your book, right? So F1 is a principal focus in case of concave lens and F2 is a principal focus in case of convex lenses, right? Here if you see, it appears that the rays are coming from the F1 principal focus, right children? Now coming to the, okay, here the object form, the size of the image is highly diminished. It is virtual and erect, okay. Object when kept between infinity and the principal axis, anywhere if you extend the principal axis, keep your object anywhere on this principal axis. It should be just between the infinity and the principal axis, anywhere in the principal axis, right? So I have kept the object over here. This is between 2f1, between the center of curvature 1 and the principal focus 1, right? So here when the object is kept, let's take the first ray which is parallel to the principal axis, get deviated, okay, after deviated, okay, after the refraction, and the second ray will definitely go just from the optical center straight, okay, and you see there is no deviation, this line is going straight, right? Now what you have to do, please produce this ray. The ray should be produced backward. The first ray should be produced backward, and wherever these two rays are meeting, after refraction, the two rays meets, okay, at the point which is between the principal focus and optical center. Now if you see the image, this image is at the same side of the object, okay, and how is the image is diminished, it is virtual, it is erect, it is between the f1 and o. So this is all about concave and convex lenses and their image formation. So let's see the conventionals. Now the sign convention for spherical lenses, where you have to pay attention, the only the focal length of convex lens, right, that has changed, and the focal length of concave lens, that has also changed, right? Rest of the signs are absolutely same. Clear? Now in case of convex lenses, the focal length, if you remember, the focal length was from the optical center to the f2, right, which is on the right side. okay, which is on the right side. So definitely this is positive. Focal length in case of convex lenses is positive, whereas focal length in case of concave lenses is negative. That is the only difference. Okay, now let's see the summary. Concave lenses, the focal length negative. In case of convex lenses, the focal length is positive. Right, the object u is the object distance, which is always negative. Because the position of object is always on the left hand side of the lens, right? So it is negative. Now in case of convex lens, it is negative. So u is negative. U is always negative, even in case of mirror and in case of lenses. So there shouldn't be any confusion. Now in case of concave lens, right, v is a image distance, right? So image was always formed on the left hand side, right? So it is negative. Okay, and virtual, right? Virtual, erect, and they are negative. In case of convex lenses, the image is formed on the other side, right? In the first 5 diagram, the image is formed on the right hand side of the lens. So images were positive, but the only case where we have kept the object between the focus f1 and o, only in that case the image is formed on the left hand side, that is on the same side of an object. So that should be considered as negative. So we have given in the diagram, it is negative. Whenever the image is formed on the left hand side, it should be considered as negative. Okay, and whenever it is formed on the right hand side of the lens, it should be considered as positive, right? Height, if it is the height of an object, okay, when it is kept on the principal axis, this should be considered as positive. When it is okay, when this should be considered as a negative height, because it is going down to the principal axis, right? From the principal axis it is going down, so this height should be considered as negative, right? So this is all about sign conventions, right? Positive signs or a sign, negative sign stands for real images, positive sign stands for virtual images. Real images are always erect, real images are always inverted, and virtual images are always erect, right, students? Yes. Now come to the lens formula. Okay, we have given the lens formula here. This lens formula is similar to the lens formula in the mirror, but the only difference is a sign difference in this, right? So m is a magnification, right? Magnification is a ratio between the height of the image and height of an object, right? And here m is also can be defined as v upon u. Children, if you remember, in case of mirror it was minus v upon u. So this, the lens the magnification formula of lenses is just opposite, that is the sign is not the same. Here the sign is positive v upon u, or just v upon u, right? So u is image distance, v is object distance, f is focal distance, right? So this was about magnification. Now this is about the lens formula. Lens formula, over here again there is a change in sign, right? 1 upon v minus 1 upon u is equals to 1 upon f, or else you want to write 1 upon f is equals to 1 upon v minus 1 upon u. Okay, it's 1 upon f is equals to 1 upon v minus 1 upon u, whereas in case of, this is in case of lens, right? In case of mirror it was 1 upon f is equals to 1 upon v plus 1 upon u. Right, children? This was a case of mirror. Mirrors, fine. So when you are writing note, please write both the formulas together, so that it can be easily understand, or else you can just remember the formula, image formula of mirror and the magnification formula of mirror, and just opposite of that formula is the formula of lenses. Okay, so this is what you have to know. The positive sign shows that the image is erect and virtual, we have discussed, and the negative sign shows the image is inverted and real. So okay, so this is a magnification, V upon U is a magnification formula of lens, whereas minus V upon U was the magnification formula, right, of mirrors, right? Am I mirrors? Fine. So this is what you have to know. Okay, you have to pay attention when you are doing numericals, children. Now let's do the power of lenses. The power of lenses is the degree of convergence or the divergence. The degree of convergence and divergence of light ray achieved by the lens is known as power of lenses, right? How much the ray is converged, how much the ray is diverged. Okay, so that is nothing but the power of lenses. It is defined as the reciprocal of focal length and represented by the capital letter P. Okay, if F is given in meter, then P is power of lens, right? It is represented by the capital letter P, right? It is given that it is a reciprocal of focal length. So P is equals to 1 upon F, which is nothing but the reciprocal of focal length, right? But when the F is given, okay, when the F is given in centimeter, then what will happen? Then you have to use this formula. P is equals to 100 upon F. Clear, students? So P will be 100 upon F. Clear? If the F is given in meters, so you can directly put the value of F and calculate the power. But if it is given in centimeter, so you need to use this formula instead of this. Okay, because 1 centimeter is equals to 1 upon 100 meter. So when you write 1 upon 100 meter here, it will get reciprocate, 100 will go up and focal length is there. So it will be 100 upon F. SI unit of power of the lens is diopter, denoted by D. And diopter, how to define one diopter? So one diopter is the power of a lens whose focal length is 1 meter. Now let me explain you. Okay. Now if I take the diopter 1 meter, focal length is 1 meter. So which formula am I going to use? This formula, right, children? So P is equals to 1 upon F. The value of F is 1. So if you cut this, what am I getting? I am getting 1 here. Okay. So this, what is this? 1 diopter. Why I am writing diopter? Because unit of power is D. So what is 1D? 1 diopter. 1 diopter is the power of a lens whose focal length is 1 meter. So we did this and we proved it, right? Now let's take the another example. If the focal length of a lens is given 2 meter, okay, so which formula you have to use? This formula, okay, when the focus is given in meter, right? So I will directly apply the formula and substitute the value. Okay, so 1 upon 2. So what is 1 upon 2? 1 upon 2 is 0.5. 1 divided by 2 is 0.5 diopter, right? So this will be my answer. Clear? And in case of the focal length, in case if the focal length is given in centimeter, then you will be getting you have to use this formula, right? Suppose the focal length is given as okay, 5 centimeter. Focal length is given 5 centimeter. So which formula you have to use? P is equals to, okay, 100 upon 5. Clear? So what will you get? You will get 20 D, 20 diopter. So here are the two ways where you can find the power of lens. Okay, children? Now here comes the power of convex lens is always positive. You must have heard that the people say that my power is 0.75, or someone says that it's plus 1, or someone says that it's minus 1.2, right? So what do you mean by positive and negative signs here, right? The power of convex lens is positive. Power of convex lens is always positive. Now why it is always positive? Why? Because if you see the rays over here, okay, they are converging. Because they are converging and meeting at particular point which is closer, okay, that is why we take that the power of convex lens is positive. Clear? And one more thing, this f is on the right hand side. This f is on the right hand side, right? If this is a Cartesian, right, then this will be on the x-axis. So this f is on right hand side, which is f is a positive. That is why the power of convex lens is considered as positive, right? In case of concave lenses, if you see these rays are diverging and they are meeting at the on the left hand side, right? Okay, here the focal point is negative, left hand side is negative. So that is why, since the focal or the focus is negative, focal length is negative, so that is why, that is the reason the power of concave lens is negative, right? Or if any optical instrument has many lenses, I have shown one optical instrument here. I think you can identify this. This is a, what is this, children? Microscope, right? And this is there is a lens over here. Over here there is a lens, right? And there is a lens over here also, right? So why are we using, first, why are we using two lenses here? Very conceptual question. Okay, so if you are using more than one lens, 2, 3, 4 lenses, it means you are going to get more sharper image, right? To get exact and sharper image, it is better to use different lenses of different magnification and power, right? So if an optical instrument has many lenses, then the net power will be P is equals to P1 plus P2 plus P3, right? So this is what given. This is how you can calculate the net power of the instrument, optical instrument. Okay. Now this is all about today's session, children. So much practice today's topic.